Okay, off we go. Gosh. Should have cleared my throat before I started. A quick reminder, I know it's been a while, spring break and all, so don't forget about the attendance quiz, code on the board, etc. What we were talking about last time was some kind of a general construction. This is going to apply very broadly to a bunch of different theorems we're going to talk about. Reminder of what's underneath all of this is that all of the theorems that we're going to talk about, they're going to make use of the idea that I'm about to show you. Yeah, they're actually all the same theorem anyway. Right, in some sense. There's special cases, anyway, of the same general theorem that's beyond what we can talk about in this course. But anyway, so that's why there are these strong connections. So back into how we're going to see this in this class, we're going to think about this idea of a quantity defined on areas. Namely, if you give me a two-dimensional region, right, then a quantity is some value that you can define for that region, for, whatever region, right? For example, given whatever region you give me, I can ask the question, how much mass is in that region, right? I can ask, what's the perimeter of that region? Namely the length of the circumference of that region. And various, who knows what else quantity you might define on regions. So, we then talked about this idea of an accumulating quantity. And this is a really important idea. I think this is about where we left off last time. But an accumulating quantity is a very special kind of quantity. It's a quantity where disjoint unions add, namely the whole is the sum of the parts. Right? And so, for example, notice mass has this feature, right? If you have some region that has mass distributed throughout the region and you cut it into two pieces, the whole is the sum of the parts. That's how mass works, right? Population, another nice example. If you have some region of land and you want to talk about the total population of let's say people on that land, well, if you split it into pieces, the whole is the sum of the parts, right? It's this obvious sort of thing. But do keep in mind, not everything has this feature. Just because you can define it for a region doesn't mean that it accumulates on that region, right? And so perimeter is a lovely example, right? The perimeter of the whole is less than the perimeter of the sums of the perimeters of the parts. Right, so not equal, not an accumulating quantity. Okay. All right. So that's where we left off last time. Here's a pretty cool point of view that you can take. I want to emphasize this is a point of view that you can take. You don't have to, right? But this is a point of view that you can take, and I think it's extremely helpful to choose to take the following point of view in a lot of cases that we're going to be seeing as we go along. So anyway, just keep in mind this is a sort of an optional point of view. But when you have an accumulating quantity, you can think of that quantity as being kind of like a stuff. You can think of it as being kind of mass-like. It's just some sort of substance that's distributed over the area, even if it isn't really particularly, defined that way. Even if it's actually something that you might think of in a totally different sense. So, for example, here's a region, right? And I can talk about, for example, how much work would it take for me to clean the floor? Let's say that's, the floor, or I feel the way I draw it looks like more like the bottom of a pool, right? Something like that. But anyway, if I needed to get down on my hands and knees with a toothbrush and clean all of that area, how much work would it take for me to do that? I don't think of work as being a stuff. I don't view it as being a substance. But you can. Right? In the following sense. If I were to say, look, the amount of work that is located in that little subregion is, well, however much work it would take to clean that subregion. Right? And so I can view that amount of work as being physically there. even though it's not physically anywhere. Work has units of energy, right? It doesn't have a location. But I can think of it as having a location. And it all works out because if you make this choice, and again, I emphasize, this is a choice. If you choose to do this, if you choose to take this point of view, everything works out because the amount of work that it takes to clean that region and the amount of work it takes to clean that and the amount of work that it takes to clean that and the amount of work it takes to clean that, et cetera, will add up to the total amount of work because the whole is the sum of the parts. It's an accumulating quantity. So the big punchline here, again, not that you have to, but any accumulating quantity you can think of as a physical stuff. Not that it is, but you can think of it that way, that it's stuff distributed over the area and nothing goes wrong. Right? This is a reasonable, self-consistent point of view. Now, just for the contrast of it all, let's go back and think about a non-accumulating quantity, perimeter. And I just want to point out how silly the suggestion that I have down here would be if I tried to apply this idea to the non-accumulating quantity of perimeter. If I were to say, okay, well, let's see, looking at the whole, here's the perimeter of the whole. What do you think would be a reasonable point of view on the question of, hey, how much of that perimeter should I think of as being within that little sub-rectangle? And the whole thing is absolutely nonsense, preposterous. It doesn't make any sense, right? Not only is the perimeter nowhere near there, right? It's not associated with that little sub-region at all. But furthermore, if you did, it wouldn't add up. If I were to say, well, whatever the perimeter of that little sub-region is, I'm going to view that much of the total perimeter as being in that little square. Well, when you add that up, you get too much perimeter. It just doesn't work. It doesn't make any sense. This is a terrible crash and burn. So, again, I emphasize, this idea is exclusive to accumulating quantities. That you can view accumulating quantities as physical stuff distributed over the interior. It's a really nice point of view, and it's going to give us a lot of convenience. So now, related idea. This, I claim, gives us an ability to extend the idea of what we mean by density. Now, I've already done a little bit of that. We've previously talked about density as being, in high school, you saw density presented as mass per unit volume. Right? Now we've broadened that a little bit, and we've thought about it as, you can have mass distributed over areas. So you can talk about mass per unit area. Or you can talk about mass distributed over a curve. And talk about mass per unit length. Right? And we have also talked about other kinds of quantities like population. Right? So not only have we made sense out of mass density before, but we've made sense out of population density. We can now actually make sense out of what I'm going to call, for example, work density. That's kind of a new idea, right? But the point is, if I were to write down seemingly the analogous formula, namely how much stuff per unit size, and if I were to try to make sense out of, well, yeah, but what do you mean by how much stuff is in some little rectangle? Well, how much stuff is in that rectangle? We now have a choice of how we can choose to view how much of the total stuff is in that sub-rectangle, even though it's not actually physically there. Right? So that is going to end up being a powerful idea. The fact that I can make sense out of stuff having a location allows me to write down this notion of a density, namely, if I want to compute work, well, work is work per unit area times area. Okay. Because it's an accumulating quantity. Okay. All right. Now, work is not actually our goal here. This is not going to be the accumulating quantity we're most interested in. I like this as an example here because it's weird enough that it kind of gets at the point I'm trying to make, but it's also still kind of relatable and hopefully satisfying that, yeah, I mean, if I've got to vacuum the floor in this room, well, the amount of work it would take me to do the left side, plus the amount of work it would take me to do the right side, is how much work it would take me to do the whole. So, okay. All right. Well, once you have an idea of a density, then you've got an integral theorem. So just in the same way that we would observe mass being an accumulating quantity, the whole is the sum of the parts, we can then further say, yeah, and mass is mass per unit area times area. Namely, because we have this associated density, we can write that down, and now we have mass computed as an integral. Right, and we've used that a bunch of times. Y'all have seen that before. The new version of this, the new integral theorem that we haven't really quite written down necessarily, is work also has this feature that it's an accumulating quantity. That too, the whole is the sum of the parts. And in analogous ways, I can say, yeah, well, work is work per unit area times area. And if I have work density given, then that allows me to compute total work as an integral. And again, not because work is the point here. What we're going to find the most valuable is that there are going to be other accumulating quantities. And I'm going to show you one in just a few minutes. But other accumulating quantities, the fact that I can view those weird, you're going to see them in a minute, weird quantities, the mere fact that they accumulate is going to allow me, just like this, to define an associated density, and just like this, to write down an associated integral theorem. And big examples coming, one today and then several more over the rest of this course. Okay, so for whatever it's worth, sometimes I call these accumulation theorems because it all follows, every result that we're going to write down in one of these theorems results from the fact that the quantity accumulates. It all comes down to accumulation. I also sometimes call them density theorems because, well, the integrand is a density. And so that kind of makes sense as well. It's just terminology, so whatever. Okay, and then by the way, likewise for quantities that accumulate over different kinds of regions. So we've talked about areas. We've talked about two-dimensional regions, mostly because our first example is going to be a two-dimensional region example. But you can just as well talk about quantities that accumulate over volumes. Right? So for example, if I write this down, what this is saying is the whole is the sum of the parts. Namely, this is how you would write down that some quantity defined on volumes is an accumulating quantity. Okay. All right. Okay, and likewise on lengths, likewise on curves, etc. Okay. All right. So let's see here. All right, here we go. So we're gonna start developing, there's like I say, a surprising example of this that works in 2 dimensions. And we're going to have to build up to it a little bit. There is some terminology and conventions that I need to get established before we can do it. So a little bit of background work. I need to define now what I mean by boundary. Now, I'm sure y'all heard the word boundary before. No big deal. Boundary is it's kind of like the border between what's in the set and what's not in the set, right? You might say it's the edge of the region, something like that. So no big deal. And one thing y'all have seen before, I'm sure, is that, for example, if I have some two-dimensional region like this, then we've thought previously of the boundary as being, well, a curve, kind of like that. Right? The purple curve is the boundary of the green region. Okay. Here's the new bit. I now have to think of boundaries as being oriented. In order for what I'm about to do to actually work out, we're going to establish a new convention. And by the way, this convention applies for most of the rest of this course. The word boundary, when you see the word boundary, anywhere in chapter 6 or 7, when you see the word boundary, that is no longer just a set. Now it is a oriented set. So in particular, it needs to be an oriented curve. I'm going to have to establish which direction is the direction to go around that boundary. And of course, there's two different choices. Right? You look at this picture that I've got on the screen here, that green region, well, I could go what you might call counterclockwise, as I have it drawn, or I could, I suppose, go clockwise around that boundary, right? It's like a little road. There's two different ways that you can go on the road. So we need to establish a convention to be consistent. Going forward, when I say the word boundary, which of these two possible orientations do we mean? And here's the answer. The answer is, let's see if I can do this right. Given some region, and I'm only drawing part of the region there, looking at the boundary curve, and again, that's just part of that boundary curve. Given that region, given that boundary curve, the orientation, the direction that you should go along that boundary curve, this is the new convention, always go in whichever direction puts the region whose boundary you're talking about on your left. So now imagine, use your geometric imagination, if you go this way, if you go, as I've indicated with this dark blue arrow, as you walk in that direction, notice, the region is on your left. And so that's the direction that you should go. It's an arbitrary choice. This was kind of pulled out of thin air, but it was pulled out of thin air a couple hundred years ago, and so just for consistency, and we've all got to be on the same page, right? Whenever you make a choice of a convention, it's very valuable for everybody to have made the same choice. Otherwise, everybody's off by a minus sign. It's super confusing. So this is an arbitrary but highly standardized and therefore not optional convention. Okay, so not just to point out, let's suppose that I went the other way, and let's just be clear about why the other way is not going to work, at least according to this convention. If I were to say, hey, I want to go that way, let's say from that point, I want to go that way. Well, as I go that way, the region's on my right, not my left. So that direction does not follow the convention. Okay. Now, there is a temptation. By the way, notice in this next example here, again, you go that way so that the region is on your left. And again, imagine yourself walking in the blue direction. The red indication is of the region being on your left. Okay. Here's a common misstatement, a common misunderstanding. A lot of people will make the mistake of thinking, well, look, here's your region. It doesn't really matter how it's shaped. The boundary always goes around the outside. And as you're going around the outside, isn't it always the case, no matter where you are on that boundary, that counterclockwise, just think about the geometry, counterclockwise will always put the region on your left, doesn't it? So it's very tempting, very common mistake for people to say that the orientation on the boundary is counterclockwise. Very common misstatement, and this is not always true. It's true for the outside part of the boundary, just like it looks like it would be. But notice, if we were to play that game with this region over here, so now I'm not going to shade in this whole region, it just would take too long. But that region there, let's talk about the boundary. Well, the boundary is not just the outside. There's also boundary kind of representing the little cutouts here. Right? We kind of have three different curves, in a sense, that make up the boundary of this green region. And notice, wrong color. Notice that wherever you might happen to be, the direction that you would go to put the region on your left, right? That's the direction you would that would be on your left. And notice that that direction is not counterclockwise. If anything, I think we'd have to call that clockwise. Okay, so anyway, heads up, that's just a warning. Make sure that you don't fall for the oversimplification that it's always counterclockwise. That's true, again, when you're going around the outside part of the boundary, not true in general. Yeah?
Yeah, I was just wondering if there's a specific reason why, like, I know I think you said it was somewhat arbitrary, but is there any reason why it wouldn't have been possible to find, like, the boundaries always being counterclockwise oriented?
Nope.
Okay.
Nope, yeah, it was basically an arbitrary choice. And it's one of these things where, the choice has to get made. Otherwise, we're all speaking a different language. So yeah, there's nothing magic about being on the left. That's a great question. And it bothers some students. But this is arbitrary. Yeah, okay, right, sure. Lots of stuff is arbitrary. Right?
I was just wondering if there was some secret reason why it would all blow up if you made everything.
No, it's, I hear you.
Okay.
But it's, I'm going to call it basically arbitrary. Yeah. Okay, yeah. All right, so moving along. So we have this new notion of what we mean by the word boundary. Reminder, henceforth, when you hear this word boundary, you need to think, ooh, that's an oriented thing. What's the correct orientation? Oh, wait a minute, how did that convention work again? And you have to not only get the right orientation, you have to remember to entertain that question in the first place. Right? So boundaries are now oriented things. Okay. All right, so with all of that said, here's my new accumulating quantity. And this is weird. This comes seemingly out of nowhere. It's amazing that this works. Boundary circulation. Boundary circulation is an accumulating quantity. The whole is the sum of the parts. And it doesn't feel like it ought to work. Let me try to convince you first that this does. By the way, this is with the understanding that you have some established vector field. So let a vector field be given and fixed, and then, given that vector field, we can talk about, for any closed curve, we can talk about boundary circulation. So, okay, well, let's see here. Here's the left region. I've got a union of two pieces, and, here's the left region. The boundary circulation around the left, now being careful to follow the orientation convention for what a boundary is. You got to be careful about that. The orientation matters, right? But so for the left region, boundary circulation would be an integral on this dark green curve. That's for the region on the left. Now let's look at the region on the right. This region on the right here, I can talk about its boundary. I can talk about its boundary circulation, therefore, and again, following the rules, always go in whichever direction puts the region whose boundary circulation you're interested in, puts that region on the left, which it is. I got to go that way to put the region on my left. So that is the oriented curve over which you would do this circulation, right? So the green integral represents the left boundary circulation. The blue integral represents the right side boundary circulation. Now let's look at the whole. The whole is this whole great big monstrosity, and the that's fine. The boundary goes kind of this order, if you will. So the boundary circulation of the whole is that integral, and we now ask the usual question: is the whole the sum of the parts? Does green plus blue give us purple? And it doesn't look like it. There's that stuff in the middle. In fact, this kind of smacks of why perimeter doesn't work, right? Perimeter is not an accumulating quantity. It just doesn't work. The whole is not the sum of the parts when you're looking at perimeter. We kind of see the same sort of problem happening here. It doesn't actually make a problem though. And here's why. If you go ahead, let's go ahead and cancel the stuff that really does kind of obviously work out. I mean, all of this stuff, there's purple terms that cancel with the green terms, and there's purple terms that cancel with the blue term. All that stuff tracks. That just makes perfect sense. It works out fine. Oh, whoops. Ooh, yeah, I erased too much. But that is going to be left over, and that is going to be left over. That's the discrepancy. That's the problem. That would be the reason why the accumulation doesn't work. But here's the thing. That's the exact same curve, line integral over exact same curve computed twice, but with opposite orientations. And we remember from previously that when you go with opposite orientations, you get exact negative answers. And so in the sum, those cancel. And there's nothing left. And so the discrepancy is 0. So this is an accumulating quantity. Boundary circulation, the whole is the sum of the parts. And the whole is the sum of the parts, all because on shared edges, whenever you have a shared edge, you're going to be going across that shared edge twice with opposite orientations, and it'll cancel. Okay. By the way, let's take a quick minute to recognize, cut it up into as many pieces as you want. Doesn't matter. Cut it up into a bazillion little pieces. And let's see here. So I have a starter kind of, if I can get this thing to cooperate. There we go. Here's kind of a, for example. And I've got some region here. And we've got the boundary curve like that. And now let's think about, how I would represent the parts on this. And, on this region, the boundary circulation on that region is like this. And now let's look at the next region. Let's see here. On the next region, on this region here, the boundary circulation is, wrong tool. Boundary circulation is like that. And what happens when I add up this purple integral and that orange integral? And by the way, I'll be adding up a bunch of other of these little small boundary circulations as well. Yeah, but on this shared edge right there, on that shared edge, I'm going that way as part of the boundary of the left. I'm going that way as part of the boundary of the right. Same integral, opposite orientations, opposite signs, they cancel. And likewise everywhere else. This edge, wrong color. This edge cancels. This edge cancels. That edge cancels. Practically all of these edges, they just keep canceling over and over again. All of the interior edges cancel. Just like in this picture here. Everybody on board? A little surprising. But we've got ourselves a new accumulating quantity. Now I want to remind y'all why, what's the point? And going back to all of this discussion that we had back here, why do we care about accumulating quantities? We care about accumulating quantities because I can think of them as stuff for which there is an associated density, an integral of which gives me a corresponding integral theorem, and I can turn the mere fact of something being an accumulating quantity, I can just snap my fingers and say, okay, well, therefore I have a corresponding theorem. Accumulating quantity means theorem. Quantity is integral of density. And that's what we're going to do here. We've got this idea of an accumulating quantity. So it behaves like stuff. It's going to be computed as an integral of a density. By the way, I can tell you what the density is. Going back, reminding ourselves, our quantity is circulation, boundary circulation. Given a vector field, of course, we have to assume that there's some vector field that we're applying this to. Given a vector field, boundary circulation has density, and for whatever that vector field is, here's the formula. The density of this accumulating quantity called circulation is computed by that formula. It's the x partial of q minus the y partial of p. That's the formula. Now, why is this formula true? It's a lovely calculation. It's in the book. If you're curious, I will confess that the details of how you compute that are important mathematically. As for how important are they for you in your future in engineering, a case to be made, yeah, maybe not so much. So if you're curious, feel free to look at that proof. It's a lovely proof. It's a cool argument, but I'm not going to require that as part of this course. I frankly feel it's a little bit of a distraction, but this is the result. Far more important to me than that you know where this came from is that you know how to interpret it. That this thing is the density associated to the accumulating quantity called circulation. That's a much more important concept to have digested. Okay, so circulation density, that formula. Now, I'm sorry to report, there's a bunch of different notations that get used for this. There's a notation proliferation problem. I'm a part of the problem, by the way. I had a wild idea about 10 or 15 years ago that here's what I think it should be called. And so anyway, whatever. So I'm going to start with what I think is the most common terminology and notation for this is this right here, curl. So y'all may remember that term from back in chapter 3. I threw out a formula called curl and said, well, we'll talk about what it means later. And here we are. So this is what curl is. It's circulation density. It's circulation around little regions per unit area of those regions. Like, again, you can define for any accumulating quantity. Okay, now another common choice is to call it rot, R-O-T, short for rotation. There's a good reason for that too, and I kind of like that terminology as well. But it's not as common, you won't see it as much, but you will see it. It's out there, so heads up, when you see R-O-T, that's short for rotation, and it's just an alternative term for curl. Here's another one. Now, I think this one is not so common, at least it hasn't been common in my experience. But this is kind of neat that, I don't know if y'all remember, but we made a passing reference back in chapter 1 to this thing called the wedge product in 2 dimensions. And it turns out that del wedge F, if you just write that down and interpret in the only way that it would possibly make sense, oh my gosh, son of a gun, it gives you exactly curl. It's wild. So anyway, this is another neat notation, and you will see this as well. This is going to be used at least a little bit in this course. So heads up, when you see del wedge, you do need to be able to interpret that as curl. All right, so, my wild idea was to call this Green's operator. And the reason why is because this density, this curl, that formula, is it's the integrand in this theorem called Green's theorem. And so Green's operator just, I don't know, that's appealed to me as a natural thing to call it. And related to that, I abbreviated by GRN. I just made that up as far as I can recall. It's possible that I was inspired by something I saw somewhere else, but that's, if that were the case, that was so long ago that I've forgotten. Anyway, in my old exams, you're going to see GRN a few times here and there. That's probably the only place you will see GRN. So, anyway, just be aware, and after you leave this course, probably don't need to know anything about it. last notation I'm going to mention, our book, in at least one place, writes it as del cross f dot k. And this one really bugs me. Y'all will recall cross product as a binary operation only makes sense in 3 dimensions. We are looking at a 2-dimensional vector field on a 2-dimensional space. We're not in 3 dimensions. Cross product doesn't make any sense. The only way that this makes any sense at all is if you say, okay, well, let's just kind of tack on comma 0, call this p comma q comma 0, like you could just do that, right? But if you did do that, and if you did compute the curl, and if you were to dot with 0, 0, 1, in fact, you would get dq dx minus dp dy. So in terms of a computational formula, it works, but there's some sloppiness going on there, and I don't see the advantage, right? So I think this is a bad choice. I very much prefer that you do not use this notation. I don't see what the advantage. What do you buy? What do you get from that notation that isn't, more easily written down? For example, with del wedge, boom, right? Very compact. Curl. Very common and very compact, right? There's nothing gained, and I think the sloppiness is something lost. So, I discourage that. Okay. All right. So, with all of that in mind, here's our integral theorem. And by the way, to be clear, this is the same integral theorem, same construction as we got here. We observe that the whole is the sum of the parts. We interpret the quantity on parts in relation to density. Done. So that's all I've got here. We have this quantity called circulation, which I'm going to denote by lowercase Greek letter sigma. Pretty common choice, by the way. That quantity is an accumulating quantity. The whole is the sum of the parts. There you go. I just wrote that down. And then, again, we make the observation that can be computed in terms of density. And keep in mind, circulation density, if I can fit this all in, circulation density is curl, aka that formula, aka whichever other notations you might prefer. And altogether then, notice all I've done is make that accumulation argument, and we've got ourselves a theorem. So what it says, and it's pretty surprising when you just look for it out of context, right? If you just look at this right here that says a boundary line integral, a boundary vector line integral can be computed with a double integral over the interior, it's pretty wild. It's pretty unexpected. Like, what? How could, but the interior, there's a bunch of points in the interior where crazy stuff can happen that the boundary doesn't know anything about. How could this possibly work? But it does. And again, it's just this observation about accumulation. Okay, how are we doing? Is everybody buying it? All right, so this is called Green's theorem. This is our first big vector calculus theorem. I've given it to you from a point of view that I think is the ultimately most intuitively satisfying. If you want to have some sense for why this is true. And by the way, I want to freely acknowledge, it takes time for these ideas to soak in. Give yourself that time. I am not expecting that this all will just be perfectly satisfying and intuitive just, in the space of the 45-minute or 40 minutes that we've been talking about it, or probably less. Take time, right? Let it steep, right? Try to compare this to the integral theorem we wrote down for work. Compare to the integral theorem we wrote down for mass. Right? Persuade yourself that this isn't mass, but it's an accumulating quantity, so I can view it as a kind of a stuff. Then the pieces kind of fit together. It's ultimately not that surprising, but I think only if you take that sort of that right point of view. Okay. All right. Okay, and by the way, this does also give us some satisfaction about what I previously claimed. Now, y'all will recall that we previously talked about curl. Again, chapter 3. And I made this assertion, completely unsubstantiated assertion, that curl, in a sense, it measures how much there's kind of a rotational aspect of the fluid in some sense. And, I didn't really have the tools to write that down. So, now we can totally make sense out of why curl tells you in some sense about the rotation of the fluid. Because curl, being circulation density, circulation, we've already discussed. Circulation tells you literally over the boundary of some region how much the fluid is following along that curve. And if you just kind of watch what my hands are doing here, the extent to which the fluid follows the curve, that represents the fluid actually kind of rotating in some sense. That represents if your fluid were lying flat and you had a leaf, and if the leaf were literally rotating, that's because of circulation. So circulation density is just saying, okay, there's going to be a little bit of circulation, and how much of that circulation is happening locally near a given point. So that is why curl, in some sense, represents how the fluid is rotating. So this that kind of closes a gap that we left back in chapter 3. Okay, let's do one. First example. Here's the question. I've got a curve given. Here it is. There's my curve, clockwise oriented unit circle. I have a vector field given, and I want to compute the integral of that vector field, vector line integral, that is, of that vector field over that curve. And now let's forget about Green's theorem for the moment. Let's just take a moment to think about how we would do this, the old-fashioned way, right? 6.1 style. Well, I'm going to have to parameterize. Okay. Well, you parameterize x and y are going to be cosine and sine. Oh, no, wait, clockwise, so let's say sine and cosine. Plug in x and y as sine and cosine into that vector field, and you get a pretty weird formula. Plug that in and do the pullback in the usual way, you're going to get a pretty far out, weird, inconvenient vector line integral to punch up. And those integrals stink. You're not going to like it. So that's a bad way to do the problem. I'm not saying it can't be done. I'm saying you're not going to like it. Right? So that would be the bad way to do it. Let's use now our powerful tools. And ultimately, this is a pretty straightforward computation. Now, there's a little hiccup at the beginning. Our clockwise oriented unit circle, I have to recognize, is not a boundary. By the way, this represents a very common mistake made when using Green's theorem. And just a reminder, Green's theorem says that these two things are equal. Notice, very importantly, this only works for boundaries. Very, very, very important little detail, Devil. It's got to be a boundary. In fact, it's only because it's a boundary that we can even talk about boundary circulation as being an accumulating quantity. And the fact that it was a boundary was central to making the accumulation work. Right? So this result critically only applies to boundaries. And I'll remind you, we have these very finicky, sticky rules about boundaries, and in particular, boundaries have to go in the particular direction, which in a great many cases is counterclockwise. Right? And that's not what we're seeing. That's not what we're seeing in this example. This is not counterclockwise, it's clockwise. So the theorem doesn't apply, and this would seem to be a dead end, but it's not. It's just a hiccup. The cool observation is that this is just the opposite orientation of the counterclockwise curve that is, in fact, a boundary. It's the boundary of D, this kind of yellow region in there. So we're just off by a minus sign. And by the way, this sort of thing happens a lot. And you know, heads up, and it's your job to be on the lookout and to, be aware and to notice when this situation happens. But my curve is just oriented the wrong way. This curve that I care about is not a boundary, but I can relate it to a curve C minus here that is a boundary. Oh gosh, I guess I'll put the happy face next to it there. That curve is a boundary, and it's oriented the opposite way, so I fix it with a minus sign. No problem. Is everybody good? We just kind of sidestep that orientation issue. So we were asked about the clockwise oriented unit circle. We threw in a minus sign and say, I like the counterclockwise oriented unit circle better. The counterclockwise oriented unit circle is literally a boundary. Straight up. No asterisk. Orientation and all. That counterclockwise oriented unit circle is a boundary. Don't forget the minus sign. Carries along, of course. And now I can apply Green's theorem. Let me get rid of the mess here. I can totally apply Green's theorem to that curve, right? This integral around that green curve, being as it is a boundary, there's Green's theorem. Snap my fingers, right? Citing the big theorem on the previous page. And this question about a line integral has now turned into a question about a double integral. And here's where awesome is about to happen. We compute curl, and curl of this vector field. Let's see here. This vector field, if you plug it into the formula for curl, it is 2. Totally awesome, right? So the fact that a line integral turned into a double integral isn't really quite. I mean, that's burying the lead. What happened is an integral with a nightmare domain has turned into an integral with about the simplest possible. I meant integram. Let me say that over again. An integral with a nightmare integram has turned into a new integral with an easy, almost as easy as possible integram. That's the big win. Right? That integram is super convenient. And now it's all over with the shouting. We have a double integral of 2 over a garden variety geometric figure. It's just constant times the area, blah, blah. And we get our answer. And of course, therefore, what we were interested in the first place. And it's just minus 2 pi. So we didn't have to deal with massive amounts of ugliness. Green's theorem made that all just disappear in a puff of smoke. Gone, not our problem anymore. Totally awesome theorem. Is everybody okay? All right. Let's see here. I'm going to be quick with this next example. I know we're short on time. Now the big idea here is I've got this curve, and it's made up of these line segments. And that's kind of weird. It's vaguely a boundary, but not exactly. What you're going to notice is that I do have the boundary of this region, D1, right? But then I also have this curve. That's not a boundary of D2. It's going the wrong way. The region's on my right, not my left. But the only problem is the orientation. And as long as I fix right, what I have there, I can recognize that that second part of the curve C is just an oppositely oriented, let's see here, boundary of this region D2. The orange curve is the boundary of that dark blue D2 region. Oh, except for the orientation. So acknowledge that with a little minus sign superscript. I got the orientation wrong. And so I've got everything written in terms of boundaries. And so with this in mind, again, it's just a matter of writing down the details. We've got this curve being recognized as two pieces of curve. Right? We've got sort of the left half and the right half. On the right half, I factor out the orientation issue, and I am left with a couple of boundary line integrals, a couple of boundary circulations. And so here's Green's theorem applied to D1, and here is Green's theorem applied to D2. Do notice you got to carry through your minus sign, right? Don't forget that minus sign. It's important, right? Orientations are a big deal. Now, again, good news. The curl turns out to be easy to compute. Wrong color. Curl is easy to compute. Again, we get easy line integrals, blah, 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 and the answer is 0. And again, no fuss, no muss. We didn't have to integrate really anything. It just kind of all fell in our laps. So another really nice example using Green's theorem. Okay, we're out of time. We'll pick up here on, oh, wait a minute, not Friday. We have an exam Friday. Don't forget about the exam. I'm sure you all remembered. But see you on Friday for the exam. We'll pick up here on Monday. Give me just 1 second.